Hi and welcome to this next clip in this acid and alkali series. In the previous clip we were using Ka for a weak acid in order to calculate the pH of that acid. Now in this clip what we are going to do is come up with a way whereby we can actually determine what that Ka value is so that we can then subsequently use it in calculations. Now, the only way we can generate a Ka for a weak acid is to do an experiment. That experiment involves us taking a sample of the weak acid, so typically 25 centimeters cubed, and essentially setting up a titration whereby we titrate it against, for example, sodium hydroxide, and we monitor the pH. Now, what we would experience is typically for a weak acid, it might start off at, say, pH 3, 4, depending on the concentration, and what we would see is that the pH would rise slightly, it would then plateau through the buffer region, and we would then get this typical vertical section whereby we get a rapid pH change which then subsequently starts to level off. And if you were to do a titration of weak acid versus a strong alkali, you would get this typical profile. And what we can see from this curve is that the value we would typically appreciate as the end point for a titration when we did them in year 12 perhaps was that this is the point at which an indicator changes upon the addition of one drop. If we'd had values which were similar concentrations and 25 centimeters cubed of the initial acid, we might imagine this would be something in the region of 25 mils itself. And this would, as we say, this would be the end point for the titration, or something which we can also call the equivalence point. And at this point in the equation, we have a situation where the H plus ion concentration has been entirely neutralized by the hydroxide ions. To all intents and purposes, they have at that point cancelled each other out. And if we were to use one of our lower school definitions of saying acid plus base gives salt plus water, at this point we only have the salt plus water, and we would have what we would term a neutral solution. Now, at that point, we obviously don't have any hydrogen ions left, we don't have any parent acid left. All we have is our concentration of salt that we've prepared as the product typically of an acid-base reaction. But if we were to take a different point on this curve, and typically this would be at a value equal to what's called the half equivalence point. So if we take our 25 centimeters cubed and half it, we go to the half equivalence point, so 25 will be halved to 12.5. At this precise moment in time, we can establish that we have probably neutralized half of the acid, and so have half of the acid remaining. If we have therefore reacted half of the acid away, we have produced the same amount of base, or the same amount of product in that reaction. Obviously our hydrogen ion is unknown because that's what we're ultimately trying to calculate via the pH. But at this very precise point, this half neutralization point, this half equivalence point, we know, importantly, that the concentration of the acid I have left to react is exactly equal to the concentration of the salt, ethanoate in this example, of the reaction that I have produced. And so if we have a Ka which by definition is equal to H plus concentration multiplied by, we'll use ethanoic acid again as its example, the ethanoate ion divided by ethanoic acid concentration. And if Ka is defined by this equation, and we have the very precise point whereby the ethanoate ion concentration equals the ethanoic acid concentration, i.e. this one and this one, if they are both the same, they will effectively cancel each other out in that equation. That then means that at this precise point, we have an equilibrium constant which has now been simplified to Ka equals H plus. And if we know that if we take the minus log base 10 of H plus, we generate the pH. If we do the minus log base 10 of both sides, I'll just take that out there, so I spelled log wrong. So if we take the minus log base 10 of Ka and we do the same of H plus, then what we have here is a very special situation whereby the value called the pKa equals the pH at that very precise point in the titration, which means if I can plot my titration curve and I can calculate where my half equivalence point is, so I know it's at 12.5 centimeters cubed of volume added in this example. If I then subsequently read off the pH and get a value, that value is equal to pH, because that's the scale on the axis, but I know that here pH equals pKa. And as we saw in the previous example, we then know that the Ka can be expressed in the same way as H plus ions can be expressed in relation to pH. Ka is equal to 10 to the minus of that pKa value, allowing us to graphically and through experimentation calculate a value for the Ka of the acid that we have titrated. And we can do this via experiment for each weak acid, which we can then subsequently use in the calculations as we did in the previous clip. This is an experiment which generates the Ka value, and as we said, Ka can only be determined via this titration method. And for students studying AQA, this is one of the required practicals and is a very common question asking you to evaluate Ka and stating the assumptions of knowing that the concentrations of the parent acid and the salt of that reaction are at that point equal concentrations, allowing the Ka equation to be simplified down, subsequently allowing the reading off of the pH equaling the pKa value at that precise point. And those values that you'll see if you were to search on the internet for Ka values and pKa values have been generated in this manner. So in the next clip, we'll take these further forward and we'll look at calculating the pHs after additions and after subsequent reactions, where if we add a small amount of things, moving ourselves towards situations whereby we start discussing buffers and also the use of indicators in titrations as well. So thank you for this one, and I will see you in the next one along.